Hello, as you said, my name is Pedro. You also know me as FG, and I'm here to talk about EFI, which is hopefully an interesting talk for you to learn some new tricks. Let me introduce you. Usually you think people know you, but some don't know you. I'm an economist by training. I'm not a practicing economist. I love human behavior, especially a branch of economics, a new one, which is called behavioral economics. It's a very interesting branch if you like this stuff. It's not mostly on social engineering, it's more on human behavior, so it's really interesting stuff. I like a lot of politics. If you do the bad mistake of following me on Twitter, you'll see a lot of noise about politics. This is a very interesting branch in Europe. And I like a bit of computers since my life has been spent playing with these tiny machines. I work these days for this company, Sentinel-1. Some of you might have heard about it on 2 weeks ago, an article about Netflix. Netflix is saying they are replacing their AV with our stuff, which is next-gen AV. I built the Mac version, the initial Mac version of our product together with another colleague. These days I'm just doing research and random stuff and solving some problems of the development team. So I'm not developing anymore this stuff, but it's still an interesting product, and if you want, you can go to the website and understand a bit more about this. So what is this presentation about? It's a very long presentation. If you follow me, I always do very long presentations, go over time and so on. She was telling me I don't have enough time for my presentation, so I'll have to skip some parts. You excuse me, you can then check the slides and see more stuff that I might skip. I want to introduce you to EFI. Most of this stuff is also applied to EFI, which is the next version of this. I want to show you how to reverse EFI binaries. As I told you, most of this information will be applicable to UEFIs, small changes and so on, but if you have the basic knowledge, you can get into this. And hopefully, I will try to teach you how to search for these kind of rootkits because they are really interesting, and there are not many samples of these because no one is looking for them. Assumptions of this presentation, I work with this machine, MacBook Retina 10.1. It's a very easy machine to work with EFI. There are some very specifics about this machine, especially on file contents, but most of the things apply to all other machines, even normal PC laptops, so it's not a big problem. I'm talking only about 64-bit versions because OS X since Lion changed to 64 bits, so I'm not interested in 32 bits operating systems. That is not anymore relevant in the Mac world. And we are also talking about only the Sandy Bridge or newer chipsets because the older versions don't have the flash protections. So it's really easy to get into there from userland. So those machines are totally insecure, and if you still use them, just forget about those. So why EFI? Why is EFI a very interesting thing for hacking? It's the BIOS replacement. BIOS is a very old thing. It's really annoying. It was different to every vendor had their own stuff, and it wasn't very powerful. It has limitations in many aspects. So Intel started developing a replacement, which is EFI. You can go on this URL. You have all the documentation, all the initial documentation. Intel stopped developing EFI on version 1.10, 1.12. And they passed control to a consortium, which is where UEFI came from. UEFI has a lot of new features, for example, secure boot, that you have big fights on Windows and Linux about this. They are starting to develop a new standard for example, booting images from HTTP instead of the old PXE and all that stuff. So it's a very interesting thing to play around. The documentation for EFI is really long. You have documents with 2,000 pages and so on. Initially, it's very annoying to get into that stuff. After a while, you know where to start looking at stuff, and it makes it easier. So EFI, like BIOS, initializes your machine. It takes control very early in the process. It has access to every low-level features on your CPU, SMM, and all kind of stuff, and the devices. It talks to all the hardware devices. So it's very low access. It is very modular. EFI was designed so you can add modules. For example, you want to have your EFI talking HTTP to somewhere, you can add this. This feature is just being added. It's feature rich. For example, you can have file systems on there talking to different file systems. Apple did this because they wanted to add HFS to talk to their file system. They added this on a driver on EFI, on their EFI for this. You can add passwords, all kinds of stuff. You can even put a game. There's a guy that created the game for EFI, so you can do a lot of stuff. It's very easy to develop for it, or it's not as difficult as BIOS because you can develop most of the stuff in C. There's a SDK, Tiano Core EDK, posted by Intel. It's open source. It doesn't contain everything. For example, the stuff for power management and some proprietary stuff, it's not out. You can get that stuff because 2 years ago or 3 years ago, there was a hack on AmiTrend and Trend BIOS site, and they stole all the code. I cannot tell you where that code is. If you go on internet, you can find this code. It's very interesting code because you can have the power management and all features that are not on EDK or Tiano Core. They are there, and you can see a lot of interesting stuff. You have code there for Sandy Bridge and Ivory Bridge and some other chipsets. So if you want to get into EFI, I tell you to try to get that package. The interesting stuff, what can we do? What can we hack on EFI? We can do diskless rootkits. We can persist across system reinstalls. Essentially, like the hard disk rootkit, you can reinstall Windows, Linux, macOS as many times you want, and we still have control if we have this kind of rootkit. We can bypass full disk encryption and so on. It's your creativity, whatever you want to think about it. For example, a rootkit, you can put a rootkit in the flash chip. It's basically another driver that contains data. You can encrypt that data. Then when the machine boots, you unpack that data. You patch the kernel. You have this presentation by Snare in 2012 at CSCAN. It shows how to implement this. So before the kernel boots, you patch the kernel. You put some trampoline there, you patch the kernel, and you take control of the kernel. And you never need to go to the hard disk. So this is a rootkit, RAM-only rootkit. If you like volatility, I have a spat or a row with the volatility guys because it's a nice product, but it has some flaws because they don't focus a lot on these anti-forensics. If you are having a rootkit as low level as this one, you can simply patch their driver. When they load their driver, you patch it and you say, yeah, my rootkit is not here, and you continue running. So there are some problems. With these, always question your assumptions, what the tool is doing. Always question that someone can do this, someone smarter is thinking ahead of you, or question the assumptions of the tools that you are trying to use so they can bypass you. These guys, hacking team, they were on the news some time ago. They were the first ones that I know that built an EFI rootkit. You can find the sources here. It's still online. This is the most interesting file from the source. Implements a lot of stuff and the core of the file. And their only goal was to persist across reinstalls. Essentially, the target that they infected, if the target reinstalled Windows, they will detect that and reinstall again the rootkit. They did something really nice, which was porting an NTFS driver into their rootkit, so they can access the file system directly from EFI. They reinstall their malware, and that's it. They're not doing anything such as anti-forensics. It's a very simple rootkit. They write to the disk, so if you have from some kind of checksum software running on the hard disk, you can detect this. But most of the targets are not technological people, so this probably works without any problems. Attacking full disk encryption. At least on Macs, the file vault password is available on boot. So what you can do, you install a keylogger on EFI. When the machine boots, you are capturing those keys, and they can recover the file vault password. Because if you have full disk encryption, you cannot attack the file system before it's decrypted. But with this, it's easy. This is an image from the Thunderstrike presentation from CCC last year. You can see this is passing control from EFI to the operating system, and he managed to capture the password for the file vault. For example, you can do an attack if you have a target, you don't need to install a rootkit, you just want to install the password, you install this keylogger, you get the password, that's it. If you have a copy before of the machine, for example, on the hotel, you have a copy of the hard disk, you install a rootkit, you get the password, you send the password somewhere, that's it, you get access to the data that was encrypted. So be careful about this model, about this type of attacks. Full disk encryption is nice, but it doesn't solve all the problems. Another one, Tails. There's a lot of fuss about Tails. It's a secure operating system because it runs from a read-only medium, but it cannot do anything against the hardware. If you have a rootkit, you have an example on this YouTube link. This is a video from the Legba Core guys, which is basically the guys that do the most of the work on EFI. Check their work, it's really worth it. And they show how to recover PGP keys from memory and the passphrases from Tails. So Tails is not that secure. If you don't have a secure machine, Tails will not do anything to protect you against this stuff. You can do some tricks on the bootloader. This is much simpler, not very complicated. You attack the bootloader, you change to a bootloader, like some Windows malware, and that's it. These are more interesting, SMM backdoors, because these run really low level on your CPU. You have this Russian guy, Crash, a very, very nice guy. He wrote a very complete post about how to build this kind of backdoors, attacking EFI with some EFI bugs that were reported some time ago. Oops, sorry. So the conclusion, if you control EFI, you control the machine, and that's it, the end of the story. And this is why I want to do this presentation. I want to call your attention for EFI, and probably you should start researching on this stuff. Let me briefly tell you a story about a zero-day. Some months ago, I published a zero-day that made some funny headlines. This is my favorite: Apple hacker reveals cracker zero-day rootkit whacker. The register always gets really nice headlines. It was essentially a firmware-related zero-day. At the time, I published it because I thought Apple already knew about the bug, so yeah, it's full disclosure. I don't care. You have a very nice post that I wrote describing the issue, all the details, if you are interested in more details. Essentially, the problem was a failure to lock the flash. In theory, you should not be able to access the flash chip from the user land. Because if you can access, as long as you have root access, you install a kernel extension, a kernel driver in your machine, you talk to the flash, you write an EFI rootkit from there, and it's game over because you control the EFI. If you follow the Thunderstrike presentation, this kind of attacks had the same effect. You just, in this case, you had to plug an Ethernet Thunderbolt adapter on the machine. He was attacking Trammel, was attacking the option ROM. From the option ROM access, he had access to EFI. He can rewrite the EFI, and that's it. The difference is that the Thunderstrike requires physical access. You need to plug in the Thunderbolt adapter. He made the Thunderstrike 2 at Black Hat, which is another variation of this attack, because you can put a worm on that. The difference, Katie labeled this bug Prince Army. I didn't label at the time. The difference is that this one allows remote attack. If you have, for example, a browser exploit chain, you get from the browser code execution in the browser, then you get local privilege escalation to root, and then you can talk to the EFI, you install a rootkit, everything remote, nothing physical, so it's very powerful, this kind of bugs. Snare, I was looking at old stuff, and Snare in 2012 was describing that he could do the same on his old machine. So he was saying that he could write from the OS, and this is really awesome because you just need an exploit chain. And the problem was that he was using one of those old machines, the one previously, before Sandy Breach, and those ones don't have flash protections. So this was the reason why he could write from the operating system. It's very extremely simple to trigger the bug. You just close your machine, you get the machine on sleep, and the machine will unlock when you get back the machine. It was unlock the flash. So not a very complicated super exploits, rope exploit, nothing, just close the machine. You could do the same with this command, just put the machine to sleep, and end of the story. At the time when I found this in March or something, all my machines were Sandy Bridge or Ivy Bridge. And then I asked the friend, let me test on your machine to see if this works on your machines. And it didn't work. And this is the reason why I thought Apple knows about the bug, so there's no problem in going full disclosure with this. As I told you, the older machines are all vulnerable, so they don't matter. What happens is that Apple patched the bug by luck because Intel patched the bug on the reference firmware, and this is the reason why the newer machines have the bug patched. They finally released updates for all the machines that are affected. If you want, then after this, I didn't know at the time when I disclosed why things were really happening. I had a very good idea, but I didn't know really what was happening. I wrote a really long post about this, reversing EFI. It can complement this presentation, so you probably want to go there and see. It has some more details. I have also links to the most important EFI documentation, so you don't need to go to the whole documentation. These docs build a very nice foundation to get into EFI. There was another vulnerability, the Venamis, which is one that you could access the S3 boot script, which is a very powerful thing. And essentially, the vulnerability is you install a kernel driver, you attack the script, the boot script that is somewhere in memory, you unlock the flash, and you can do whatever you can want. It requires a bit more complexity because you need to install a kernel driver and the script and so on, but it achieves the same results as this bug. But the story doesn't end here. Apple just patched one of the bugs or two of the bugs. The Thunderstrike 2 guys presented a few more bugs. You have these nice shards, so they patched this one. They also patched parts of the S3 script because they didn't fully patch everything that is required. But they still have another vulnerabilities in EFI-related stuff. So this slide, the guys from Legbocord and Trammell were putting this argument. Apple is not as responsible to fixing this kind of firmware bugs, which is a bit annoying because they have a very focused, limited hardware, and they can really patch faster than everyone else. So I usually like this slide. Apple, they are potheads. I have a fight with them, and they never patch things too fast, and it's really annoying. So let me tell you where is EFI inside your computer so you can start doing some reversing on this stuff. It's a serial flash chip that you can find on your motherboard. This is one of the chips. It's usually a SOIC, in a SOIC format, this one, with 8 pins exposed, so it's very easy to plug in with a SOIC clip. These are the two popular modules on older machines. It talks SPI. This is very nice because it's very easy to talk to this. And most of the newer chips are 8 megabytes. The older ones are 2 megabytes. There are some new machines that have 128 megabits. I'm not sure why. Probably it was cheaper for Apple to buy those. Where it is located. This is my machine, a Rutina 10.1. This is where the chip is. So the only thing that you need to access the chip, you just take off the downside cover, and you access the chip. It's very easy. Always unplug the power because you don't want power to be running on the same as you are dumping the chip. But the problem is with other machines. For example, here, this is a chip for a MacBook Air. You have to disassemble the whole machine to access the chip. On a Mac Mini, it's the same thing. It's very packed. You have to disassemble, and the chip is here. This is on a Mac Pro. I have a Mac Pro. The first thing I did when it arrived, so you have like a 4 or 5K machine, the first thing you do is open and disassemble the machine. And the first thing I did, okay, I reassembled the machine, it didn't boot, and I was thinking, okay, I just destroyed the 4K machine. Luckily, it was one of these bugs. These was a new kind of buzz from Apple, and it wasn't really settled. So, okay, You disassemble again, assemble again, it boots, okay, it's safe. But you need to disassemble a bit of the machine. In this case, the Mac Pro is nice because the machine is really well constructed, so it's a nice thing to disassemble. This is one of my, I have an Macintosh computer, which is basically a desktop PC running macOS. My motherboard is a Gigabyte, and I wanted to dump my EFIs. They have dual BIOS. If you go, there's a presentation from Legable Core saying that this is bullshit. Gigabyte says, oh, if this is wrong, this one will act and save you from virus. They have shown that is total bullshit. What you see, it's very difficult to dump the BIOS because you have the pins from the cooler, and I had to bend my pins on my motherboard to access the ports. So the thing is that it's not always easy to access the EFI, and this creates a problem. For example, if you are at a company, you cannot be disassembling all the computers every month to check for rootkits. So this presents a really problem for checking this. But with some practice, for example, I have another machine that I need to disassemble. I already can disassemble the machine in 5 minutes or less. So, for example, if you leave the machine on your hotel room, 10 minutes is enough to rootkit your machine, open, disassemble, access the EFI, reflash, and assemble again. So be careful with that. The timings, with some practice, can be really low. As I told you, most of the chips are 8-pin. The newer versions, I don't have these machines, but I saw the pictures and I cannot identify any SOIC clip that reminds me of a flash. They appear to be SMD or BGA versions, which is very annoying because they don't have pins exposed. So you have to unsolder this. You need a hot gun, hot hair gun to unsolder this, which is annoying. You have to unsolder to dump, you have to solder again, and this is not very practice, and you can destroy your machine. So it's really annoying that this is not happening. So you can find this chip. This is the new chip, Winbound, that they're using. And if you dump the strings on the flasher for the updates, you have all the chips, the list of all the chips that Apple uses on their machines. Something you can do, you can buy this from the AliExpress. AliExpress is a really nice site because everything is cheap and you can buy bulk. So what you can do is you can buy these chips for testing. I recommend you because it's very interesting. You want to try something to see if your flasher is working and so on. You buy these chips like $14 for 10 chips, and you can use them for testing. If you, for example, mess up your chip on your machine, you can replace with one of these. So, first important step after locating the chip is how to dump the chip. Hardware, there are two ways. You can dump from hardware. This is why I'm interested on the pins. This is the most reliable way. The machine is powered off. Nothing is interacting because you are removing power. It's trustable dump because you are connecting to the SPI port. You are reading directly from the chip. Unless you can really mess up the chip, hardware is not my specialty. Unless you can really find a way to, when what you are asking the chip to give you is wrong, it's trustable. And you can also dump this from software. It's possible if it's supported by flash ROM. There's another way because Mac shadows the BIOS on physical memory, so if you know where that is, it's not very difficult to find it. You can also dump from there, but be careful, it's just a copy, a shadow copy, so it could be modified by someone. So it's not very trustable dump because if the rootkit has anti-forensics, you don't know what's really in there, you cannot trust that. What you need for hardware? You need an SPI programmer. Flash ROM has a bunch of those programmers. What I use is the Trammell Hudson's SPI flasher. He built something based on Teensy. The first attempt I did with EFI was with the Buzz Pirate. Don't do that, it takes a long to dump. I gave up on EFI. I started with EFI in like 2013. I wanted to dump it. It took like 2 hours to dump, 4 hours to write. This is not scalable to do research, basically testing stuff. If it takes 2 hours to test bit change, it's impossible to do anything. You have all the schematics here, a post here on SPI. As I told you, it's based on Teensy 2.0 or 3.0 or 0.1. The Teensy 2.0 is not anymore available, the official ones. You can buy Chinese clones that work also well. It's very easy to build. It costs you like $30 everything, the Teensy, the cables, and the soy clip. It's really fast. You can dump 64 megabit in 8 minutes. This makes things really faster for research. It dumps in 8 minutes. It writes in 11, 12. Trammell told me that the Teensy 3 version is even faster because it's a better CPU. It's an ARM CPU. For me, it just works. And since I'm an economist, if it works for me, I don't care anymore about the problem. Let me skip this. This is the pinout stuff that if you want to build your own version, you have all the pinouts that you need. The Teensy 2, just something. The Teensy 2, the voltage is 5 volts. The SPI on these chips is 3.3. So you just need to buy a voltage regulator, solder it to the Teensy, and you solve the problem. The Teensy 3 doesn't have the same problem because the default is 3.3 and not 5. Just a small tip and trick. You should shunt the write protect and the reset pins to the VCC. If you don't do this, you run into some problems with the chip. It doesn't power on, and you have to take the clip out and the clip on. If you shunt the pins, it works. So it's some of the things, okay, I don't care why it works, it just works and that's it. SPI, you have many different names for pins. I just left this because I had to search them. Some documentation talks about the MOSI, others about the DO, DOut. It's a mess. I don't know why it's not just the same thing. This is just some comments. Most of you, I'm not sure if you are old school enough, Trammell uses X modem. This is really old. To dump, he has a Teensy program. It talks to the chip and gets the data via X modem, and that's it. As you can see, my dump here took 7 minutes, so it's really fast. Outright, basically you tell the area. This is my version, which has a bit more options on the firmware because I was trying some stuff, so I just wrote that code. Essentially, you say I want to write the whole BIOS from 0 to the size, in this case 8 megabytes size, and use this command, the PV, which is uploads directly to the port and flashes. I'm not sure, I didn't research this issue yet. If you try to flash to read from OS X, it works okay. If you try to write, you run into some problems. I use Linux to write, so I have just another laptop just for writes. I think it's either a PV or a serial driver issue. You can try to solve it, but at least Linux works for this, so if you run into problems, you already know why. For software, you can use FlashROM. There's this driver, direct hardware, that talks, basically it's a driver to use the ports, talk to the ports on Intel. You also have this utility, RW mem by Trammell. This one can read the flash, the shadow area because it only reads memory. It doesn't talk to the pin like FlashROM does. I did also this read physical mem. I will just show you why. You can find both FlashROM and direct hardware kernel extension on this package, Darwin Dumper, if you don't want to compile. This version is a kernel extension if you are worried, okay, this might contain some rootkit or something because you don't know this code. The code is not code signed, but Apple trusts this. There's a whitelist by Apple that kernel extensions that they say they trust. So Apple says this one is okay. It's just a matter of trusting Apple or not. These are the links where you can find this stuff. To dump it, you load the kernel extension, and then you use FlashROM to read the dump. You use the internal flash because FlashROM recognizes the chipset. FlashROM identifies. It starts looking for all the chips that it knows. It finally found, in this case, a Micron chip, gets some of the characteristics of the chip, and then finally dumps the chip. It's really fast. It takes like 1 minute or two to dump. And it has the same dump, 8 megabytes are there without any problem. This kernel extension is default on Apple. If you saw my last presentation, I was using this kernel extension to install rootkits on the machine because Apple put a kernel extension that talks directly to the physical memory on the machine without any access other than root. So you can talk to this and ask, read me physical memory from this and there. So you can use this to read the BIOS from the shadow area without installing the direct hardware kernel extension. This extension is default on Mavericks and Yosemite. They finally canceled this. Well, what they did is blacklist this kernel extension. So they are saying, we don't trust anymore our own software. I'm not sure, they finally released the Gold Master yesterday or 2 days before. I'm not sure if what they are going to do this. At least on betas, they finally blocked this because it would be an obvious bypass, for example, to the new future rootless. You would just talk to this extension and kill rootless from the kernel. So the point from software is good enough if you want to start. You don't have hardware and you want to dump and play with some things. It's, as I told you, useless to chase rootkits unless they are made by hacking team, because those guys don't make any attempt to hide themselves from software dumps. I don't like hacking team. I make fun of them, so I'm always trying to attack them. Contents on the flash. You get a binary dump, what's in there. There are different regions and there are different versions of this. This is one of the simple one. It has a descriptor region that says what's inside the BIOS. Then you have Intel management, which is shared with on the BIOS chip for cost reasons. This is a big black box. I was talking with Pod2G, what are the next directions on research? There are 2 things that I want, SMC and this one, because this one is very powerful. And then you have the BIOS region that contains everything EFI related. Another version, you have the descriptor, you have the gigabit region. This is another region that is shared with the onboard cards. And again, by cost reasons. I'm not sure where is the document, but I think it's an Intel document that says, okay, we map this inside the same chip because cost reasons and the bill of materials goes down. There is this new region, platform data. It's binary data. I'm not sure what it does. It's not really important, I think. So this is the contents. As you can see, the descriptor and the BIOS region contains all this stuff, all these files or all these volumes, EFI volumes. The contents of the platform data, as you can see, it's only raw data. I didn't research, it didn't seem to have any interesting stuff. I just want to show you what's in there. What is the descriptor region? It shows you the location of other regions. It tells you everything where everything else is. It contains access permissions. For example, you don't want your gigabyte Ethernet card being able to talk to the area where the BIOS is, because that gives you right away a rootkit hint. You attack your Ethernet card, you flash the BIOS from the Ethernet card, and you have a nice rootkit coming from the Ethernet card. For example, the Intel, the management engine region, you also want to protect this, because this feature is really powerful. Let me show you, where is it? Here. The Intel management engine region. This is a CPU that runs inside your normal Intel CPU. The first time I saw the presentation by Igor, I was like, what? You have a CPU running inside your CPU? But the real detail is it runs Java. Crazy stuff. It can be active with the system powered off. As long as you have power on the machine, this chip can talk to the network because it has an out-of-band network access, which means that you have a MAC address inside your CPU that can talk to the network. This is a nice feature in terms of big networks because you can manage this kind of machines from the central network, but it also makes a really nice, interesting point for rootkits. As I told you, there is no access from BIOS or OS or in Siri. There is no access from there. It's mostly a big black box. As far as I know, there are only 3 presentations by Igor Skoshinsky, which works for X-Rays, the company from IDA. It definitely requires more research. If you go to see the feature sheet of Intel management, it's really powerful. And Intel doesn't open this. We don't know what really happens there. There's an unpacker. This was a really step forward. The old version couldn't unpack all the contents of Intel management. This new version can, so this is a big step for research. Igor did these three presentations. You can find them here. It's really good presentations. You should go checking them and get really scared about the second CPU that runs inside your CPU. The BIOS region. It contains EFI binaries for the different phases. It contains the non-volatile RAM. The non-volatile RAM is used, for example, to store the EFI Wi-Fi password on Macs. This is the reason why if you reinstall the machine, you see the networks that you know already there, and you ask, why the hell, where are they storing this? They store this on NVRAM. It's also stored, for example, when the machine kernel panics, they write the data to the NVRAM because the file system, you don't know in what state it is. It contains microcode, Intel microcode. I don't see these on every firmwares. I guess it's, for example, newer machines still don't have microcode updates on the first releases, so they don't pack the microcode. You can find the Intel microcode there. There's also some presentations about the one from Ben Hawks about attacking microcode, also very interesting. And there was on Troopers last year via Rigo, another presentation on this, so it's very interesting. What I told you here, I don't have it. Okay, this is what they call a firmware volume. It's basically a shell that contains files. So these are the different firmware volumes that exist in that region. Everything is labeled as a Git, so you have no file names. You only have 128 bits numbers on this. You can start identifying, for example, it contains mine, this is a dump of mine, contains 2 microcode firmware volumes. I'm not sure why they duplicate, probably as a backup. You can identify the NVRAM, it's a firmware volume. You can identify the boot volumes, and these are generic volumes that contain EFI drivers. Another view of this, you have for a firmware volume, then you have another file. This is what they call files. In this case, it is compressed. You will find a lot of files are compressed to save space. And you finally have a binary, a TE binary and a PE32 binary. So the parser, if you try to write a parser, it's not very difficult to write a parser. It's just, if you try to write it in C, it's a bit annoying. It's probably C++ or something object. It's easier to describe this kind of stuff. But you have a firmware volume, and you have files, and you can have files inside, and you can have firmware volumes inside a firmware volume. So it gets a bit inception, and if you try to do this in C, it's a bit complicated in terms of describing. As I told you, everything is labeled as a Git. There are no file names whatsoever. You can find many in the EFI documentation, so grep or search on the PDF is your friend, and many are vendor-specific or private, which the only way you can do it is reversing stuff and understand what they are doing. This, for example, is from Snare. You got a database. There are 3 or 4 big databases of Gits that were extracted from many vendors from official documentation, so you can have some human translation to the Gits. Let me go just over really fast on the boot flow. EFI has different phases to initialize the machine. Most of the time, they make resources available to the next phase. Memory is, for example, one of the most critical. If you know some details about CPUs, your 64-bit next generation CPU still boots in 16-bit mode. It then makes resources available. It has no memory, for example. It starts making memory available for the next phase. One of the first phases is very restricted in memory. You'll see this in the type of code you see there on that phase. It's not very complex. It doesn't make a lot of things because it doesn't have a lot of memory for that. This is a very common diagram on EFI-related presentation. It shows the different phases. So you have the sec phase, which is the first phase. It basically assures that the platform is in a secure state. Then you get into the pay phase, which is the pre-EFI initialization. It takes care of making memory and stuff ready. And you have the driver execution environment, the DXC phase. This is where a lot of stuff happens, where most drivers are loaded. This is a very intensive phase. And then when it finishes, it passes control to the bootloader. This is where you see grub and whatever EFI bootloader you have. And then it continues to the operating system. The operating system, there are some services that the operating system can talk to EFI, but most stuff is closed because it's not anymore, it's not needed, so you cannot access that kind of stuff. This is the description. Just a very quick thing to explain why the DXC phase is very complex. It's a very heavy phase, so when you close down your laptop to save power or to travel or something, when you restore, you know, by spec, I think it's 2 seconds or 10 seconds, I cannot remember the number, but there's a standard when you resume your laptop, when you open, that you must respect. At least by Microsoft, I think it's 2 seconds, that the computer must be ready for use. If the computer would do again all the phases, this will take a lot of time because of this phase. So what they do, they create a script, the S3, where the bugs were, and the S3 basically has all the information on memory and puts the information that was needed from the DXC phase. It just copies. This phase is much faster. This way, you don't need to start again all the drivers. And it's basically a boot script that gets you everything ready for the machine. This is the reason why the suspend from the computer is very fast. Let me skip this. There's a dispatcher on these phases. So this is what guarantees the order of load drivers. There is not a script. There are dependencies between. So there is a dispatcher, starts loading all the stuff and understands, okay, now I have to load this because there's this dependency and so on. So let's get to the fun stuff, how to reverse. This is a set of tools, basic tools. So the two most important are this one, EFI tool. I got the screenshots from there. Because it understands the whole format. You can remove files, you can add files, you can extract files. It's a very nice tool. It takes all the work that you might have to write a whole parser. IVA is not very good reversing or understanding EFI binaries. Snare built some Python utilities to make this easier. For example, it converts the GIDs to file names, which is much easier to do. I will show you there are no direct references, no library references. Everything is a function pointer. So it also converts this to a name. It tells you, okay, this is a function name, so you don't need to go consult the tables. These are two other tools. Chipsec is not really a tool for reversing. It's a tool for analyzing the firmware security. It's a very nice tool by Intel Research. And it can tell you, for example, you load on a machine, it can tell you what security features your machine has. If you run that on gigabyte motherboards, you'll get scared because they don't lock anything on flash. I don't care, everything is open. Important things. There are two EFI file types I've shown you from that screenshot. If you don't like Windows, you are going to learn the PE format because the format that they use is PE. PE 32 plus, which is for 64-bit binaries. There's another format, the TE-TERS executable, which is essential PE with small modifications. And you'll see 16-bit, 32-bit, and 64-bit code in the binaries. Because it starts on 16-bit, goes to 32, and then finally goes to 64-bit code. So you need to reverse all different kinds of code. As I told you, TE is just a stripped version of PE. If you know the PE format, it has a lot of information that it's not really necessary to run. The first phases, as I told you, they are very restricted in terms of memory, so you want the binaries as small as possible. So what they do, they just remove the unnecessary stuff to save space, and you'll only find these two types of binaries on the second pay phase, which are the phases with restricted memory. One problem with this format, either is unable to disassemble this format because it fails to parse the headers. I have a confusion with either with X-rays, with the license problems. I reported the bug, they didn't want to fix, and so on. I'm not sure if it's still fixed, but the solution is you build your own key loader. You can build this in Python or C. I built one, it's very easy. At the time I didn't want to release, I will probably release it because enough time went by. And essentially you go to the headers, you fix stuff, you read stuff the correct way, and IDA can finally read this. It's not very difficult. This is the only problem that you have with this format. Everything else is just like PE. So if you are coming from userland, you are used to have a libc or something else to link against. EFI doesn't have anything like that. They have a concept of services, which are basically functions that a table of functions with a very limited set of things that you can do. And everything is a function pointer, as I told you, and you'll see this a lot in the code. This is one of the tables on the pay services, on the pay phase. For example, you can install another services, you can locate services, you can allocate memory, you can copy memory. This is the very limited set. With this, you can do a lot of stuff because, for example, you have another driver that installs more features. You locate that driver, you install that driver or that service, and you have more features. So basically, EFI, as I told you, is modular, so you have blocks and you keep adding blocks, and that's how easy it is. This is the runtime services when your operating system is running. You have, for example, functions to services to get time, set time. You can talk to the variables. For example, this is most probably all Linux. Linux has something like the proc system to check the EFI variables. They probably have talking to the kernel talks to EFI to this and gets the contents of the variables that are on EFI. So, as I've shown you, each phase has different services. So, how do you locate this? The entry point, the first function running on the binary, always has a pointer to one of the tables that you can get this information for. In this case, you have to the system table. It has this structure, and you have the pointers to, in this case, this DXE binary. You have to the runtime services and to the boot services tables, so you know where to locate this. So this is why you see this code very often, or a small variation of this code on EFI binaries. What it's doing is storing local copies of the pointers. The boot services, the runtime services, and then it can reference everything from these pointers that it stores. So it's very common, this code. Talking about functions, more things that you need to know how to reverse. The 32-bit binaries use the standard C convention, so everything is passed on the stack, the arguments. This is used on the second and the pay phase binaries. This is an example. You see everything being passed on the stack, function being called, and that's it, nothing very complicated. The 64-bit binaries use the Microsoft x64 convention. So the first 4 arguments are on the register, on these 4 registers. Everything goes on the stack. There's a very small detail, very important for EFI developers that have problems when they start developing. There's a 32-byte shadow space. I cannot remember the reason I read about it, but it was not very important. So the first stack argument always starts at this offset. So don't, the first time you see it, you see these where, so where are the other arguments? They are there. They are something like this. The first 4 here on the registers, and you can see the fifth on the 32 bytes offset, and then the other one 80 bytes offset ahead. So this is just a small detail, but a very important detail if you are reversing. Really quick on this. As I told you, there are no libc on EFI. What you have is the services. The basic services are the ones from those tables, and you can ask for more services from other drivers. They call it protocols and PPIs. The PPIs are the ones from the pay phase, and protocols are the ones from the DXC phase. They are the same thing. They call different names, I don't know why, but they are essentially the same. It's basically a data structure that contains a Git, because that's the identification on EFI. And it contains function pointers and data. Most of them contain function pointers. Others just contain a guide, for example, to signal that you loaded this driver or something like that. Very quick on this. This is a protocol. So you have the guide for the ACPI S3. Then you have the protocol itself. It contains two function pointers. And the function pointers define this. This is an object. And this is one of the parameters. And this is another parameter for this. So how do you do this? You, okay. To use, in this case, is a PPI, not a protocol, but it's the same. The first thing you do is to locate. You ask EFI, locate me this protocol. You pass the guide, the identification of the protocol, and you get a function pointer. And this is the function pointer. If everything went well, you can use the service that exists on that protocol. And this is how most of the code on EFI is like this. It's locate a protocol, get a function pointer, and use the function pointer from the service that you want. So you see a lot of code locating services and using this. And this is one of the noise of reversing EFI. If you don't have, for example, a snare script, everything is a function pointer. And after a while, you start memorizing all the tables. I already know some of the offsets by memory, but it's really annoying. Everything is a function pointer. Then you have to keep track of the protocol. So with some script to label everything, it's much easier than this. Let me skip this. Last important details, some Apple customizations on EFI. There is a reserved field on the header, which is this one, the zero vector. If you read the spec, it's used for the reset vector of some CPUs. Apple doesn't use this CPU, so decided to use this zero vector for some stuff. The first 8 bytes, I don't know what they mean because they are constant between everything. They change between versions. It's probably some data. If you modify it, it doesn't have any problems, so it's okay. The next 4 bytes, they are a CRC32 value of the contents. So if you modify the contents of the firmware volume, you need to update this value. This is the value there on the zero vector. So this is a CRC32 of this particular firmware volume. And the last 4 bytes, it was something unknown. I was trying to modify EFI firmware, and it broke the machine. What the hell is happening? So it's essentially the total space that is being used on the volume. It's the contents of this less the free space of the machine. So if you modify the firmware, if you change some of the space, you need to update this value. This tool, EFI tool, already does all this. I reported the bug to Nikolai, and he fixed this. So this tool does everything for you, so you don't need to worry. You only need to worry about this if you are building your own tool. So last but not least, how to find EFI masters. You need to dump the flash contents, open your machine, dump everything. Hardware is the best thing, as I told you. You have to have something to compare against. You either bought a machine and you trust it's okay, someone is not targeting you with the firmware rootkit, so it's not good to buy online. Or you can use the firmware updates to compare against. You can download the firmware updates from Apple, or they have a very specific page with this. When they launch major updates, sometimes they bundle the firmware updates with those, so you can extract them. Apple doesn't publish any hashes from this. I'm trying to convince them to publish this because it's important to have this. Another problem is that the comparing against updates is only useful when there's an update. For example, when they release a new machine, usually there is no update, so you need to wait for an update to compare against. I built a vault with firmwares. I extracted everything. I signed with my PGP key. So if you trust me, you have there a vault, at least something that is signed. They were extracted from Apple updates. I did my best to check signatures from the package, but I don't know if they are totally legit. And soon I will add the SMC updates because this is also very interesting. There are two formats on those updates, the SCAP and the FT. This is used on older machines, and some newer ones are also using this. I don't know why. The SCAP is something that comes from Intel. They recommend this as the delivery mechanism. It's basically something with the firmware volumes. So if you have the same parser, you can parse the SCAP. You can see here an example. This is the flasher, the binary that will flash, and this is the contents of the firmware of the updates. One thing that happens is that you don't have the same gits from the BIOS. So what you need to do, you need to parse the firmware volumes, find the gits that contain the data on the firmware volumes that are inside the flash, and you need to extract those. So it's not a direct comparison. You need to write a tool to extract the information that you want and finally compare against it. The SCAP is signed. There are a few keys inside firmware. This is not a feature from EFI, it's from UEFI, but Apple backported this. You can read the description from Thunderstrike presentation. Tremel went on this, so you can verify that signature of the SCAP, which is good. So what you need to find is you compare the flash dump against the SCAP, you extract everything, and you see if the binaries change or not. If the checksum is okay, it's at least those haven't been tampered with. If not, you might have a problem. You also need to verify if new files were added to the file system. If there are any missing files, for example, removing some security feature from the EFI, that could work. The free space, you can put some information there. For example, data, rootkit data, you can put there, locate and extract some payload. So always look at the free space, see if there is something strange there. You also should check the NVRAM contents. Why? Because hacking team, this is the way they knew if there was already installed a rootkit on the machine or not. They had basically a fuse on the machine. You also have inside the NVRAM the bootloader. In this case, in macOS, is boot.efi. One final detail I forgot to put on the slides. All the strings are multi-bytes in EFI. So if you do grep, you will not find any strings. You need something that does multi-bytes grep. Be careful with this. And this is a piece of code from a hacking team. They were reading a variable, an EFI variable, in this case the FTA variable. If the EFI was 0, they would infect the system. If it was 1, the system was already infected and do nothing. This is one of the reasons why you should check the NVRAM contents. You also might check the bootloader. This is a very simple attack. It's on the file system, so you can detect with an integrity file system tool. But this is very important. We always like sophisticated APT stuff. The simple stuff works, so be careful with the simple stuff. As I told you, the SCAP has different contents. We can build your own firmware from that. You just need to extract, build your own firmware and flash, and that's it, if you don't trust the dump that you have. Conclusions, very quick. EFI rootkits are not unicorns. Everyone talks about them. You had last year or 2 years ago, the bad BIOS thing. Everyone was making fun of Dragos. And hacking team did one in 2014. What happens is we don't really know what's out there because no one is checking. I guess I'm not a target these days for an EFI rootkit because I'm actively looking, so it wouldn't be very smart to attack me. But there are people that don't check this. There are companies that don't check this, so they could be really nice targets for this. Chasing them requires hardware. This is the only way to trust on this. I hope I have convinced you. Disassembling computers, but this creates a problem. Disassembling computers monthly is not scalable. You don't have, like, first you have to disassemble a computer, you need people. It's not efficient, it's not the best method. It's not a viable method in for example, a large company. For me, before traveling, I dump it. After arriving, I dump it again, just for interesting for me. But in a large company, this cannot work. So you have a big problem how to deal with this at enterprise level. I don't know what is the answer. We need something coming from the manufacturers or something. We need a different thing on this. Vendors are usually slow releasing updates. Apple is slow. Gigabyte is slow. They don't care. The Legba Core guys have huge fights against this. If you go see their timelines, it's like 1 year from disclosure with the vendor and nothing happened. They got some update from Dell, for example. Dell moved but took some long. So you are never sure that they will release updates. So you have one of the most important features on your computer that doesn't have updates. Scary stuff. SMC is another interesting chip. This has very access to other areas on your machine. If you look at the schematics of the SMC chip on Apple computers, it has very interesting connections. There was work 2 years ago and last year from Alex Ionescu as a nice presentation. Andrea, which will present tomorrow, also has a very interesting analysis and very interesting tricks to get content from the SMC. So it presents really interesting rootkits possibilities. This is my next chip that I'm going after. As I told you, Intel Management Engine, this is really interesting one. Probably people should start looking around at this because it will be really interesting stuff. Last, option ROMs, Thunderstrike 2. Tremel is still attacking option ROMs. The reason is there is no secure boot in Apple. Apple didn't port this feature because secure boot demands option ROMs to be signed. Option ROMs in Macs are not signed, so you can modify a Thunderbolt adapter, modify its option ROM, and make a worm out of it. Check the Thunderstrike 2 presentation. They built a worm. You plug in an infected computer, and you start distributing a physical worm through all other computers. So don't share the Thunderbolt adapters. If you know this, if you follow this, this is the thing from GCHQ destroying the computers, from The Guardian. There was a presentation at CCC Camp about this. So the question is, was GCHQ trolling everyone by destroying all the chips, saying, yeah, we are going to destroy because we are just making fun of you? Is this real? Probably is, because you've got, for example, the trackpad controller as an ARM32 or ARM16 CPU there. So you have a lot of CPUs in your machine that you have no idea. It's probably a mix of both trolling and real. Check this. I cannot give you, once again, links. I had a very nice image, but I have no idea what is the legal thing. You can find this, especially from Chinese boards. They have the schematics for most of the Apple computers. So this is really nice to have because you can see the logical connections between the chips, and you can see what are the interesting chips that you want to attack. We really need these trusted hardware solutions. Everyone, me included, is trying to solve some software problems without having hardware problems. If you cannot trust hardware, as I hope I convinced you with EFI, you cannot do anything from software. If I'm running at a lower level privilege, every software solution is doomed to be beaten from there. So we need this if we really want computers to be safe. So bring back these physical protections. If you are from old school, to flash BIOS, you'll need to get a switch. We need switches for the mic. For example, all my computers have the mic connection off. The camera is with tape. We need switches for this. I'm not sure in terms of design of the computers. It's probably complicated, but I'm not a designer, so it's their problem. But we should demand this kind of stuff. I need to activate features with physical. From software, it will not run. 2 minutes. For example, this is someone, listen, and this comes from, it's here. There's a screw. I'm not sure how they put a screw. It's probably on off. This is from Chromebook. So if you go to this page, they have some information, and they have this physical protection on the machine. So you can say, I don't want anything to write to my BIOS. This probably requires new hardware designs. As I've shown you, for example, NVRAM needs to be writable. So if you protect the chip, you have a problem. Maybe the decision is a flash chip that contains NVRAM stuff, but then you can attack NVRAM, for example, the bootloader. So there are a series of problems here. There are bill of materials, basically cost or space restrictions. If you look at Apple computers, the Retina, the smaller ones, they have a single board, so you need space. Space is very expensive there. So I'm not sure what are the solutions, but we need them. Last argument, 1 minute. Apple has a great opportunity here because they control the whole design and the supply chain. They say, I designed this computer with these features. They can improve the design. They can be the first one to do this, to do, for example, physical switches and so on. They can force faster updates because they can bundle a firmware update like they did with the fixes for my 0 day. So they have a really good opportunity to this. This opportunity is only matched by Chromebook because they are trying to do the same. They are trying to build a secure computer. They also control not the full supply chain because there are vendors doing this, but they have a great opportunity here. So firmware security is critical. I hope you are convinced about the importance of this. Some greetings to the EFI guys. Thank you, 44Con, for making it possible. My contact stuff, the only thing you need to memorize is this one, which is the address of my blog. From there, you can get everything else. You also have the GitHub with code for a lot of stuff. Feel free to contact me, to email me. I do my best to help people and share knowledge. So don't be shy talking to me. If I don't answer in 2 weeks, send again, because usually I get something interesting, and email is on the lower chain of things to do. The slides will be available just in October, but you have another version that I presented in Korea. It's not as complete as this one. You can go to the blog, and then in October, I will put the slides public. So you have a lot of references here for this. That's it. Hey,
Thank you, Pedro Vila.
Do you want to make a Q&A or no? I'm okay.
So thank you very much, and have a good lunch break. Thanks.